Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if a computer could help us build theories about how the world works, especially when things get super complicated? Well, today we're diving into a fascinating new way scientists are using something called large language models, or LLMs, to help figure out those really tricky cause. Effect relationships. So imagine trying to map out why someone feels depressed or why an addiction cycle is so hard to break. These are super complex things with so many factors interacting. Scientists have a tool called the Causal Loop Diagram, or CLD, to try and visualize these connections. Think of it like a complex web showing how different things influence each other. But building these diagrams normally takes a ton of time and brain power, especially when you are looking at lots of different pieces. This is where the magic of LLMs comes in, like the advanced AI that can write stories or answer questions. The researchers in this study created a tool called CLDassist. It is like a helpful assistant for scientists. You give it a topic, like the self-perpetuating cycle of addictive substance consumption, and it uses an LLM to help suggest and organize the potential causes and effects. It's not meant to replace the scientist, but more like a thinking partner to explore ideas and make sure they haven't missed anything. So how does it work? Well, the process is broken down into steps, almost like a recipe. First, you can ask the LLM to help you come up with a list of important factors or variables related to your topic. These variables need to be things that can actually change or vary, like frequency of substance use or intensity of cravings. They can't be vague like the environment, unless you can specify how it changes. The LLM is trained to suggest measurable and distinct variables, which is super helpful. After you have your list of variables, CLDassist then asks the LLM to figure out if there are causal relationships between them. It essentially asks, does a change in variable A actually cause a change in variable B? And it doesn't just say yes or no, it gives a probability, like there is an 80% chance that frequency of substance use causes increased cravings. This probability is like a score for how likely the LLM thinks that connection is based on all the text it is learned from. Then, if a relationship is likely causal, CLDassist asks the LLM to determine the direction of that causality. So, does substance use cause cravings, or do cravings lead to more substance use? And finally, it tries to figure out the sign of that relationship. Is it a positive connection where an increase in one leads to an increase in the other, or a negative one where an increase in one leads to a decrease in the other? Think of it like this: more studying generally leads to a better grade. That is a positive relationship, but more stress might lead to less sleep. That's a negative relationship. Once all these steps are done, CLDassist can create a visual causal loop diagram. This is where you get that web-like diagram where arrows show the direction of influence and colors or thickness might show if it is a positive or negative link and how strong that connection is thought to be. One of the really cool things this paper shows is how well these LLMs actually do compared to humans. They tested LLMs on a bunch of variable pairs and compared their judgments to what human experts thought. This is amazing. It means that for these kinds of causal judgments, the LLMs are doing about as well as human experts agree with each other. That's a huge deal for speeding up research. The paper also highlights how this can help with really massive problems. Imagine trying to map out all 113 DSM symptoms for mental disorders. Doing that manually would take nearly 44 days of continuous work for experts. CLDassist can generate an initial diagram for that in just one day. But, and this is a crucial but, these LLMs aren't perfect. They can sometimes make things up, called hallucinations. And they can carry biases from the huge amounts of text they learn from. That's why the CLDassist tool also includes a function to search for literature that supports these relationships. This is like a fact-checking step. It helps researchers see if the LLM suggestions are backed up by real scientific studies or if they're just plausible-sounding ideas. The researchers emphasize that this tool is meant to assist experts, not replace them. The human touch, the critical evaluation, and the deep domain knowledge are still absolutely essential. So, what does this mean for us? It means that the pace of scientific discovery might speed up. Significantly complex problems that were too daunting to even start mapping out could become more manageable. Imagine using this for understanding the spread of diseases, figuring out better ways to tackle climate change, or even understanding the complex causes of mental health issues more deeply. It's like giving scientists a super-powered magnifying glass and an organized notebook all in one. The biggest limitation, as the authors point out, is that LLMs aren't perfect. They can still be wrong, they can still be biased, and they don't actually understand causality in the way a human scientist does. They're pattern matching machines. So, while the agreement with humans is impressive, that doesn't mean an LLM-generated CLD is automatically true. It is a starting point. It can highlight potential connections we might have missed or spark new ideas. But a human expert still needs to dive deep, critically assess the evidence, and ultimately make the final judgment. They also suggest future research could involve fine-tuning LLMs for specific research areas, or even allowing users to connect their own literature collections to the model for even more personalized and grounded results. This research bridges a really exciting gap, showing how cutting-edge AI can be a powerful ally in the fundamental human endeavor of understanding the world through careful, structured theory building. What do you think about using AI to help build scientific theories? Let us know in the comments below. If you found this breakdown helpful, give this video a thumbs up, subscribe to Rubin's Mind Lab for more science explained simply, and hit that notification bell so you don't miss our next exploration into the fascinating world of the mind. Thanks for watching, and we'll see you in the next one.